Hello, welcome everyone warmly. We are starting another series, Twisting Round Rods. I hope this series will be popular because twisting round rods is a topic that appears in virtually all studies, in every engineering study field. The first topic will be statically determinate examples. We will start with such an example. We have a two-stage rod with dimensions. Today we have given a diameter of 6 centimeters. It has been permanently attached at the left end and loaded with twisting moments of 20 and 30 km, as shown in the drawing. We have adopted a Kirchhoff's modulus of 80 GPa. Calculate and draw diagrams of twisting moments, shear stresses, and the angle of twist. This is what the rod looks like. Here we have D, here is twice the diameter, 2 moments, and we're off. The first thing I want to show you is that you can encounter different notations. That is, it can be written in the form I have presented here, or it can also be in the form of moment vectors. So the vectors drawn here are in the plane perpendicular to the page, and you can also make an equivalent notation and mark it this way. Now we need to, of course, be oriented on whether the moment marked here in the drawing is positive, meaning in line with the marked x-axis, or negative. According to the right-hand rule, if you take your hand, arrange it in this moment, like wrapping your fingers on direction, in this way, if you wrap this moment, your thumb shows you the direction of the moment. So, as you arrange your hand, it's like you want to embrace this moment, and then your thumb shows you that the direction of the moment is to the left, which is why this 20 is directed to the left here. Now, if you wanted to embrace this moment with your hand, the fingers won't show you the direction in which this moment rotates. They will show the opposite direction. And to embrace this moment, we need to direct the hand in the opposite direction. Then we rotate the whole hand in the direction the 30 km moment rotates. And then the thumb shows us a direction in line with the x-axis. So here we have a direction in line with the x-axis, which are two equivalent notations for such a task content. Another problem that can arise is that I have encountered at least different notations. What do I mean? From where do we start considering the force? Here it is clearly defined on this drawing on the left that here in cross-section C, it is perpendicular, this vector is perpendicular to this page so it is clearly in cross-section C. Here it is equally clearly in cross-section B, and when we start marking it with arrows, someone might ask, from where does this force start, or does it start from here? And I have encountered different notations. I drew this vector in this way, and I usually try to stick to it, that the force starts from the moment where it is attached. So here we have the 30 attached, so I will count it from here. Here we have the 20 attached, so I will count it from here. It matters, for instance, if a vector was drawn here, the question is whether we start counting it from where the force is applied, or maybe from where the moment's direction ends. And I've come across various notations, but you should always be guided by how the intervals are drawn at the bottom, and then we will know. Well, all right, now for the signs. When we have assumed the x-axis to the right, the positive moments are outward of the section, and negative are inward. If we had the x-axis direction marked to the left, it would be the opposite. Positive inward, negative outward. Now we can finish this theoretical introduction. Let's make a cut from the right side. So here there's still the moment in the entrenchment, of course, but just like with the cantilever beam, we don't have to calculate the reactions in the entrenchment. It's enough to move from the right side and not reach the entrenchment. And I will do so. We won't be calculating the entrenchment moment. So we make a cut like on the beam, meaning from this imaginary cut left we discard everything and look only from the right side and see only this moment. Well, there might be a problem with this notation because let's say I cut it like this, and I still see a piece of the arrow, and that's what I was talking about. But this moment only, its force starts only here. Alright, so we have a negative 20 in this section, meaning in section BC. We have in section BC, this is negative 20 kNm. Then I make another cut. Here, a bit crooked, but here. So I look from the left side, I look from the right side. And I see negative 20 and positive 30, so in total that's plus 10 kNm. And that's all. We can already draw the moment diagram, but we will do that at the end. Now, shear stresses. Shear stresses during twisting are the twisting moment over the torsional resistance indicator. The torsional resistance indicator for a circular cross-section is pi d cubed over 16. A PDF file will be attached to this course with a breakdown of resistance indicators and inertia moments of basic flat figures. What I just took, pi d cubed over 16, we have a circular cross-section, torsional resistance indicator, pi d cubed over 16. We will soon need the inertia moment indicator for torsion and S. We will take from here pi d to the 4th over 32. In future examples from the course, we will still use the circular ring. So the resistance indicator will be needed both in section BC and in section AB because the diameters are different. So the torsional resistance indicator in section BC, well, we substitute the diameter from section BC, which is 1d, meaning 6 centimeters, and it comes out to 4.24 x 10 to the minus 5. The dimension of the torsional resistance indicator is meters cubed, because here the meter is raised to the third power, and the torsional strength index of section AB. Similarly, we substitute the diameter from section AB, which is 12 centimeters, or 2x6. We get the result. Now we can calculate the shear stresses. Shear stresses on section BC. This is the torsional moment on section BC, which we have already defined here, minus 20. It was KNM, which means times 10 to the third, over the torsional strength index of this section. Here I've already substituted in meters, so I had the result in meters. Everything is in base units, so I got a very large result on the calculator because it's in the base unit, meaning here without mega, just pascals. The result is quite large. I multiply it by 10 to the minus 6 right away to have megapascals, because stresses are usually given in megapascals. And then for section AB, similarly the moment in section AB, a positive 10 to the third because kilo. Small strength index 3.39 and we get 29.5. A very large difference, but that's just this example. Now, the next thing we have to calculate, the last one. The angle of twist is the torsional moment times the length of the section. We will take the length of the specific section from the superposition over the Kirchhoff's modulus times the polar moment of inertia. The polar moment of inertia from the note I just showed. Pi d to the 4th over 32. Now we will calculate the polar moment of inertia for section BC and the polar moment of inertia for section AB. So for section BC, we take the diameter from section BC, which is 6 centimeters, and for section AB we have 12 centimeters, and we have calculated the polar moments of inertia. Now the angle of twist for section BC. We take everything from section BC, which means the torsional moment from section BC, length of section BC, which is 2m. Kirchhoff's modulus is constant for the entire length of the rod, and the moment of inertia we calculated. Now, if we want to draw the twist angle graph, it's enough to calculate the twist angle of section A, the twist angle of section B, and the twist angle of section C. Now the twist angle of section A is 0, because here the rod is fixed, there will be no twisting here. The twist angle of section B is the twist angle of section A plus the twist of the entire section AB. Similarly, the twist angle of section C is the twist angle of section B plus the twist angle of section BC. Now let's calculate section AB. We substitute the torsional moment AB 10 times 10 to the third, the length of the section 3 meters, 80 times 10 to the 9th, which is 80 GPa, and 2.04 times 10 to the minus 5, the polar moment of inertia of section AB. The result comes out in radians. We do the same for section BC. Substitute the appropriate values. The result comes out in radians. So the twist angle of section A we have already mentioned. The twist angle of section B is 0 plus phi AB, which is this amount. And the twist angle of section C is phi B plus phi BC, which totals minus 0.3754 radians. Now let's start drawing the graphs. So the moment diagram for the twisting moments in section BC here has a constant value of minus 20, and in section AB a constant positive value of 10. Well, nothing could be simpler. Then we have the angle of twist. The angle of twist is a linear function, meaning the further we move away. We wrote phi AB there, and it already included the length of 3 meters. So, the twisting moment times 3 meters, we calculated for the whole rod immediately. If we wanted to calculate halfway, we would substitute 1.5 instead of 3. If we wanted to generally create a function, then without this L we would have a function. By substituting any length from section AB, we would calculate the angle of twist at any cross-section. So this is a linear function. The values change linearly. Here is 0, here is this much, from section C is this much. We connect linearly. And we have the shear stresses left, which is on section AB positive 29.5, on section BC, negative 471.57. These are constant values, which is how the diagrams look. And that's it. It seems to me that the basics of twisting are not difficult. If anything is still unclear to you, I encourage you to ask questions below. I will definitely answer. Visit us on Facebook, like our profile. I also encourage you to visit our website where you will find many examples. And don't forget to subscribe to us. Take care, bye.